Hello and welcome to another lesson on algebraic methods. So if I have a look at the first lesson, that's been done. Now we're going to move on to having a look at what's called the Factor Theorem. As well as that, last lesson we looked at polynomial division. I did say it was quite messy and some people just really don't like this method. I personally think it's worth sticking with, but if you're in the boat where you're thinking I absolutely hate, with a capital H, the polynomial division method from last time, first lesson is for you. I'm going to show you another way where you can work out the quotient when you divide a polynomial. So Mr. Chadwick actually showed me this method, so thanks to him. I do like the method as well. So now you can, after this lesson, take your pick over which method you want to use when dividing polynomials. It's entirely up to you. So let's now start properly and have a look at the first 4 warm-up questions. It's just to get you into the groove of thinking about divisors, dividends, quotients and remainders. So try these yourselves first of all. These aren't too bad actually, and then once you're done, play the video and just double check that what you've got is correct. So let's have a look together at the solution to question 1. So question 1, it says 36 is to be divided by 4. Calculate the quotient Q, where Q equals 36 divided by 4. Okay, this is probably the easiest question you'll ever have in any warm-up. So Q is 9. The remainder is 0, because 36 divides into 4 exactly. So write 36 in the form 4 times Q plus R. So the dividend, 36, equals 4 multiplied by the quotient, which was 9, plus the remainder, which was 0, so don't need to include that at all. Part 2, only slightly harder. So write 58 divided by 7 as a mixed number. So 58 divided by 7 equals 58 on top, 7 on the bottom. How many 7s fit into 58? Well, I'm pretty sure you can fit 8 into them. 7 times 7 is 49, plus an extra 1 is 56, so the remainder is 2. So it's 8 and 2/7. For part B, it says using part A, or otherwise, state the quotient Q and remainder R when 58 is divided by 7. So for this one, the quotient is what we have here. So the quotient Q is 8. And the remainder, just be careful, it's not 2/7, the remainder is 2. So Q equals 8, and the remainder is 2. So 58 can be written in the form 7 times 8 plus 2. You might be thinking, why have I set these as a warm-up? It's just to link in from the numerical side of things to the algebraic what division means, if you like, in terms of when we divide one thing by another. It can be written in this form here, where we just have this and the remainder, or we can say that something we divide equals what you divide it by multiplied by the quotient plus the remainder. And so this works for polynomial division as well. So it's worth just linking it to the numerical side of things. Obviously, I'm not insulting your intelligence here. I'm sure you know what 58 divided by 7 is. I'm just trying to make this link to strengthen the understanding. Question 3. Divide x squared plus 3x plus 2 by x minus 1. So we're just going to use the skills we had from last lesson. So x minus 1 divided by x squared plus 3x plus 2. So let's see how much you remember from last time. So first off, we divide the x squared by the x term only here. X squared divided by x is obviously just x. Then we multiply x by x minus 1, which gives us x squared minus x. Then we subtract. So this cancels. Then 3x minus minus x is 4x. Then we bring down the next term, which happens to be the final term. We then divide 4x by the x, which gives us plus 4. So we then multiply this 4 by the x minus 1. So 4 times x minus 1 gives us 4x, and 4 times minus 1 is minus 4. Now we subtract. This cancels as ever, then 2 minus minus 4 just gives us positive 6. So therefore we can say that x squared plus 3x plus 2 divided by x minus 1 equals x plus 4 plus remainder 6 over x minus 1. Now this is where we can use the link from before when we had 58 divided by 7. So if you liken this to 58 divided by 7, how many 7s fit into 58? That was 8. In the same way, how many x minus 1s fit into this? Exactly, it was x plus 4, then remainder 6. When we do 58 divided by 7, it's 8, remainder 2 sevenths. So the denominator is still what you divided by in the first place, just as here the denominator is what we divided by here. So it still links in exactly. Another way you could write it would be to say that therefore this divided by x minus 1, if we multiply here both sides by x minus 1, we get x squared plus 3x plus 2 equals x minus 1 multiplied by this x plus 4 plus 6. And that just so happens to be the answer to warm up question 4. Question 4, we have this, which we've just answered on the previous slide for question 3. So this can be written in this form, which is this here. So A and B in our case are positive 4 and positive 6. So the idea of this warm-up is just to bring together the ideas about division, linking it from the purely numerical and seeing how it links exactly and does actually make sense with the algebra. Even though the algebra seems much more abstract and, dare I say, can seem almost nonsensical, it's hard to get your head around. Hopefully this warm-up has helped you to see that it does link in to the more familiar if you spend the time to get your head around it. Okay, let's have a look now at some bits for this lesson, the main bit. So I want to just mention, like I said at the beginning, a different approach for doing polynomial division, because the long division method, although I would strongly recommend it, it still isn't for everyone. So if you're really, really itching for a different method instead of the long division, this will be for you. So before we start, it's worth noting that when we divide a polynomial, let's call it p of x, p for polynomial, so when that's divided and the quotient and remainder are calculated, then we can express the dividend, the divided polynomial, that is, as either this way, where p of x divided by what we're dividing it by, px over the divisor, equals a quotient plus remainder over divisor. So again, like I said before, just link that back to basic numbers. So 17 divided by 5, we put here the dividend over divisor equals a quotient, 3. 5 goes into 17 3 times, remained 2. We put the remainder on top of the divisor. So that's one way it can be written. Or we can write it like this. where the polynomial is divisor multiplied by quotient plus the remainder. So link that back to whole numbers. 17 equals 5 times 3 plus 2, which we can derive from just taking this and multiplying through by the divisor. We've also seen how polynomial long division can be employed to find the quotients and remainders when polynomials are divided by linear factors of the type ax plus or minus b. Another approach is to consider the degree of the polynomial, where degree is the highest power of x. So we're going to consider the degree of the resultant polynomial after it's been divided, and then we can systematically compare coefficients. So although this sounds technical, using it is much easier than what it sounds. Just to go into a bit more of the technical details. So in general, if we've got a polynomial to be divided, which is p of x, and that has degree denoted by degree p, where the degree is just the highest power of x, and the polynomial dividing it is f of x, and f of x has degree f, and then thirdly, let the resultant polynomial of this division, the quotient, call that g of x, have degree denoted by degree of g, then what we're saying here is the degree of g is the same as the degree of p minus the degree of f. That sounds a million times harder than what it actually is. I'll illustrate this now with a couple of examples, and I promise you it will make perfect sense. So, like I'm saying, in practice, it's actually quite obvious. So if you had like a cubic, which is degree 3, because it's got an x cubed as the highest power, and if you divided that by a linear expression, degree 1, that would give you a polynomial degree 2. So a cubic divided by a linear expression will give you something which is quadratic. And we saw that in lesson 1, where we divided cubics by linear expressions. The resulting quotient was quadratic. Or you could have, say, a quintic, degree 5. If you divide that by a quadratic, which is degree 2, that would give you a cubic polynomial, which is degree 3. Degree 5 minus degree 2 equals degree 3, and so on. So this is just a useful idea, just to quickly double check if your answer makes sense. For example, if you took a cubic and divided it by something linear, and you ended up with a linear expression, you'd be wrong, because you'd know for definite you needed a quadratic. So although this looks technical, it's much easier in practice. So what we're going to do here, using this new method, I'm going to divide 6x cubed plus 28x squared minus 7x plus 15 by x plus 5. Linking back to what we said before, we start by noticing that we're dividing a cubic by a linear. So we're going to have a quadratic quotient of the standard form ax squared plus bx plus c. So we're expecting up to 3 terms when we divide. So because we're expecting 3 terms when we divide, we're going to construct a grid with 3 columns for ax squared, for bx and c, and 2 rows for what we're dividing, an x and a plus 5 is what we're dividing by. So it's going to be a 3 by 2 grid as such. Now what we do is we start off by putting what we're dividing by, the divisor, on the left. So we're going to put the x and the plus 5 here. X and plus 5. Now, what we actually do is we're going to put, or aim to put, the dividend inside here. So the dividend goes inside the grid, not on the top. And what we do is we play a game of balancing it all out. And we start with the highest power. So if we look here, the highest power of the dividend is x cubed. We want 6x cubed, so we put this in the first top left box. We put 6x cubed. Next we think, well, 6x cubed divided by x would be 6x squared. So on the top goes 6x squared. Another way you could think about it is what would I need to multiply x by to get 6x cubed? It'd have to be 6x squared. X times 6x squared equals 6x cubed. This links very, very closely to the grid method of multiplication for numbers, if you remember that, if you were taught that at GCSE. This is a grid method, but for polynomials, essentially. So now we've got 6x squared at the top, 5 at the bottom. If you multiplied those together, we'd get 6 times 5, 30, x squared. Now we need to balance it. How many x squares do we actually have? We had 28. This is too many x squareds. So to balance that out, what we're going to need to do is we're going to need to subtract 2x squareds away. Now, what would we need to multiply x by to get this, what we have here? So we can do minus 2x squared divided by x, which gives us minus 2x. So the top would need to be minus 2x. Then we multiply the minus 2x by this 5 underneath, and we get minus 10x. But how many 10x's did we need? We needed minus 7. We've got minus 10 here, so we've taken away too many x's. We need to add an extra 3x's, because minus 10x plus 3x gets us to minus 7x, which is actually what we have. Then it's the same idea again. What would I need to multiply this by? So what would I need to multiply x by to get this? So 3x would be x multiplied by positive 3. So on the top, I need positive 3. 3 times x is 3x, so that double checks, that's right. On the bottom, 3 times 5 is going to be 15. At this stage, we compare. Is that right? Is that exactly what we have here? If not, there's going to be a remainder. If it is correct, then there's no remainder, and we've divided by a factor of this polynomial. 15 matches exactly. So what this shows is that x plus 5 divides exactly into this. X plus 5, in other words, must be a factor of this polynomial. So we can conclude now. So based on this, we can say that therefore 6x cubed plus 28 x squared minus 7x plus 15 divided by x plus 5, that equals, now the answer, the quotient, is what we end up with on top. So this is our answer. So we'd end up with 6x squared minus 2x plus 3. Now, I'm always dead against forcing methods on people. So this method is great if you want to use it. It's entirely up to you. Now, if you wanted to use the previous method, which, for lack of a better word, I'm going to call the traditional method, you could have divided this by that using polynomial long division. So doing it that way, it would check out exactly the same. So here's what you would have got had you have done it using polynomial long division. As you can see, you would have ended up with exactly the same result. So that's how it works if you have no remainder, this method. But using this method, what if you had something which doesn't divide exactly and leaves you with a remainder? So let's have a look at a second example using this new method. So example 2, find the remainder when we divide 10x cubed plus 43x squared minus 10x minus 10 by 5x plus 4. So what we're dividing by, we put on the outside. I'm going to put in the divisor into these boxes. So we're going to start by putting 10x cubed in. So on the top, we need to do 10x cubed divided by 5x. 10 divided by 5 is 2. X cubed divided by x gives us x squared. So this box must be 2x squared multiplied by 4, which is 8x squared. Next, think, how many x squares do we actually need? We need 43x squared. So 43 minus 8 tells us we need actually an extra 35 to make it right. So we put 35x squared in the next box. Next up, we think, what would have multiplied 5x by to get this? In other words, to work out what goes above, we can do 35 divided by 5, which is 7, positive 7, and x squared divided by x, which is x. So on the top, we need plus 7x. This bottom box here will be 7x multiplied by 4, which is 28x. How many x's did we need? We need minus 2x's. So to go from 28x to minus 2x, we need to subtract 30x's. Now we can work out what must have gone above. So minus 30x divided by 5x leaves us with just minus 6. So this final box down below must be minus 6 times positive 4, which is negative 24. So is that what we need? We needed to have minus 10. We've actually got minus 24. When the final box doesn't match, that's when you know you've got a remainder. You work out the remainder by thinking how much over or under what we need are we? We needed minus 10. We've got minus 24, and so we're 14 short. Whatever you're short by is your remainder. And so we're short by 14 because we need to add 14 on to get to that. If this number here was bigger than what we have or needed, then we'd overshot it and our remainder would be negative because we need to take away something to get to that. But because this is less than the minus 10, the remainder is positive 14. We can directly always calculate the remainder by calculating this here minus what we had in this box. So minus 10 minus minus 24. So that's how we arrive at the remainder being 14. Again, as ever, don't let me force you into any particular method. You could have used the standard long division method, and if you had, you would have got this. The remainder would have been 14, as you can see. So do use this method and stick to it if you want. I'm not trying to force you onto another method. I'm not trying to confuse. I'm just saying if this really, really isn't for you, here's an alternative. I'll just do another quick one for you using this new method, and then we can move on, and then you can decide which method you prefer and just stick with the one method. So here, find the remainder when 4x to the power 4 plus 30x cubed minus 11x squared minus 15x plus 10 is divided by x plus 5. So this is a quartic, but you know, the same method can still apply. So we write x plus 5 here. In these boxes, we need to try and match it to this dividend. So first of all, we write down 4x4. So what would we need to multiply x by to get 4x4? That's going to be 4x cubed. So all you do here is just 4x4 divided by that to get this. So in the bottom box, we're going to have 4x cubed multiplied by 5, which gives us 20x cubed. But we need 30x cubed, so we need to add on an extra 10x cubed. So how would we get 10x cubed? We'd have to multiply this x by an extra 10x squared up here. So this bottom box is going to be 10x squared multiplied by 5, which is 50x squared. How many x squareds do we want? We actually want minus 11 of them. So 50 is way too big. To go from 50 to minus 11, what we need to subtract 61x squared. Now, we do minus 61x squared divided by x, which gives us just minus 61x. So this bottom box is going to be minus 61x times 5. Use your calculator, I'd suggest, but this will give you minus 305x. So, how many x's did we need? We want minus 15. So minus 305 is way too small. So to work out how many extra x's we need to add on, we can do minus 15 minus 305. We need to add on an extra 290 x's to get to the minus 15, which is what we need. 290 take 305 is minus 15, so that works. So what goes above this final box, we do 290x divided by x, which is positive 290. So this bottom box is going to be 290 multiplied by 5, which is 1,450. We now compare this final box to the constant. This is way too big. We've massively overshot this constant. It's too big by 1440. So to get from here to what we need to, we'd need to subtract from this to get to that. So for that reason, because we need to subtract to compensate, the remainder is negative. So the remainder is going to be 10 minus 1450, which is minus 1440. And again, if you want to choose the standard long division method, be my guest, you should have got something that looks a bit like this. So freeze the screen if you'd like to just jot that down and double check you've got it right. So that's just showing that each method is completely consistent and agrees with the other. Next up, the Factor Theorem. You need to use this and know it well for A level. You don't need to reproduce the proof of a Factor Theorem, but what I'm going to show you is that it does work, and I'm going to show you a quick proof of it. So what is the Factor Theorem? Let f of x be any polynomial. If f of a equals 0, then we're going to prove that x minus a is a factor of f of x. So if f of a is 0, then this linear expression will divide f of x exactly. We're going to also show, equivalently, that if x minus a is a factor of f of x, then f of a equals 0. So the converse of 1 is true as well. So this is if and only if. So if f of a equals 0, this is a factor. If this is a factor, f of a equals 0. These statements are equivalent. So let's have a look at number 1. So imagine you divide an f of x by a. Then f of x could be written as x minus a multiplied by the quotient plus the remainder, where q of x is a quotient and r is the remainder. Okay? So let's think about this now. If f of a equals 0, what would happen if you substituted a into this expression? What would drop out? If f of a was 0, then f of x, which is f of a, is 0 here. You then get x minus a becoming a minus a, q of a plus r. But this just becomes 0 multiplied by q of a. 0 multiplied by anything just reduces, so we're just going to be left with r. So therefore, 0 must be r. In other words, the remainder has to be 0. Because the remainder is 0, we've proven that the linear factor you're dividing by, which was x minus a, must be an exact factor of a polynomial. So therefore, if f of a is 0, that shows us that x minus a is a factor of f of x. Let's think about 2 now. So for number 2, conversely, if x minus a is a factor, then by the definition of a factor, we have no remainder when we divide by this factor. And so f of x equals x minus a qx plus r would just become f of a is a minus a qx plus r, which is 0 plus 0, because a minus a is 0, r is 0 because we're saying it's a factor, so that equals 0. And so if x minus a is a factor, f of a would have to be 0. So f of a is 0 when we substitute x equals a. And so one implies the other and vice versa. So don't dwell on the proof too much, but we do need to dwell on this important result. So what we're going to do here is, whoops, not like that. Let's see if we can change that colour. There we go. Get rid of that, in fact. Messed up there big time, never mind. So we're going to dwell on these two results. So let's have a look now and see how this works in terms of a practical setting, how to use this to answer exam type questions. So let's have a look now at an example. So now we've talked about what the factor theorem is and we've proven it, let's use it in some examples. So first of all, we have a function f of x equals x cubed plus 2x squared minus 5x minus 6. Part A, we have to use the factor theorem to show that x minus 2 is a factor of x. If x minus 2 is a factor of x, then by the factor theorem, f of 2 will have to equal 0. So let's check and validate f of 2. So when x is 2, x cubed is 2 cubed, 2x squared is 2 multiplied by 2 squared, minus 5x is minus 5 times 2, and minus 6 is obviously just minus 6. So let's just beat the examiner around the head with this to make it perfectly clear we know what we're doing. So normally I'd say just to bash this in on a calculator, but let's just show it incredibly clearly to the examiner to make sure we pick up every single mark. So 2 cubed is 8, 2 multiplied by 2 squared is 2 times 4, which is 8, minus 5 times 2, that's minus 10, minus 6 is minus 6. 8 plus 8, 16. 16 minus 10 is 6. 6 minus 6 equals 0. So we've checked it out. It works. So therefore, we can just conclude shortly by saying, therefore, x minus 2 is a factor by the factor theorem. So now we can move on to have a look at part B. So now it says, hence fully factorise f of x. So at this stage, if we know that x minus 2 is a factor, we can then divide this polynomial by x minus 2, knowing that we'll get a 0 remainder. So you can now divide it by x minus 2 using either method we've now talked through, the box method, which I've shown you before, or the standard long division method. I'm going to use the standard long division method, but of course, if you prefer, you can use the other method. So we take x minus 2, and we're going to divide that into x cubed plus 2x squared minus 5x minus 6. So first of all, we divide x cubed, whoops, go away please, x cubed, we divide it by x, which gives us x squared. Then multiply the x squared by x minus 2, so x squared times x is x cubed, x squared times minus 2 gives us minus 2x squared. Now we subtract, this column cancels, 2x squared minus 2x squared is 2x squared plus 2x squared, which gives us 4x squared. We now bring down the other term to join it, so we have 4x squared minus 5x. Now we go again and divide. So we divide 4x squared by x, which gives us just positive 4x. We now multiply 4x by x minus 2. 4x multiplied by x is 4x squared. 4x multiplied by minus 2 gives us minus 8x. Now we subtract. Minus 5x minus 8x is minus 5x plus 8x, which is 3x. And of course, you bring down this minus 6. There we go again for the last time, because we've run out of things to bring down. So 3x divided by x gives us just 3. Now we multiply 3 by x minus 2, which gives us 3x minus 6. Finally, we subtract, and as expected, we have 0 remainder, because we were dividing the polynomial by an exact factor from part A. We proved it was an exact factor by the factor theorem. So what this shows us is that this polynomial, x cubed plus 2x squared minus 5x minus 6, that equals x minus 2 multiplied by this expression we found out here. So it's that multiplied by x squared plus 4x plus 3. Now a little tip the question gave us is it said hence fully factorise. That's a slight nod to say that this might factorise again, this bracket, and it does if you look at it closely. Two numbers that multiply to 3 and add to 4 are 3 and 1. So this final bracket we can factorise into x plus 3, x plus 1. And that is the final answer. That's it fully factorised. So now let's move on and have a look at another worked example. This second worked example, we're given a polynomial again, and we're told that f of 3 equals 0. So it says, write f of x as a product of two algebraic factors. So we need to remember what the factor theorem tells us. What it tells us is if the function of a value equals 0, then x minus that value must be a factor of a function or the polynomial. So because f of 3 equals 0, we can say, therefore, that x minus 3 is a factor. So that's just using the factor theorem again. So because now we know that x minus 3 is a factor, we can divide this thing here by x minus 3 to reduce it into another algebraic factor. So if we write x minus 3, the divisor on the outside, and on the inside we write minus 2x cubed plus 11x squared minus 16x plus 3. So hopefully you're getting to know the drill by now. We take this highest term here and divide it by the highest term in x. So minus 2x cubed divided by x. First of all, that gives us minus 2x squared. Now we multiply this by that. So minus 2x squared multiplied by x minus 3 gives us minus 2x cubed. Then this multiplied by minus 3, just be a bit careful, this will give us positive 6x squared. Now we subtract, this cancels as ever. 11 minus 6x squareds leaves us with 5x squareds, and then we bring down the minus 16x from above. And now we go again. So we divide the highest power of x, in other words this one, by the highest power of x in the divisor, this one. 5x squared divided by x, that will give us positive 5x. Next, we multiply. 5x by x minus 3 gives us 5x squared minus 15x. Then we subtract. This cancels. Over here, minus 16x minus 15x is minus 16x's plus 15x's. That leaves us with minus 1x. Finally, we bring down the last term, which is plus 3. We've brought down the last term, so the next run through is going to be the last step. Minus x divided by x would give us minus 1. Now we multiply. Negative 1 multiplied by x minus 3 gives us minus x minus 1 times minus 3 goes as a plus 3, and lo and behold, as we'd expect, we're subtracting the same thing away from itself to give us a 0 remainder, which is what we'd expect, because we knew that x minus 3 was a precise factor of the polynomial. So from this, we can now say that f of x equals this factor here, which is what we were dividing by, multiplied by this quotient. So f of x equals x minus 3 multiplied by minus 2x squared plus 5x minus 1. At this point, it might just be worth making a note of the question one last time in case you're tempted to try and factorise a second bracket. The short answer is this won't factorise nicely, but the question does say write it as 2 algebraic factors. There's the first and there's the second. So that's just another reason for reading the question carefully, as if you needed another reason. To read this as 2 algebraic factors saves you from needlessly trying to do anything else with this. 1, 2, we're done. No need to worry about anything else. You can move on to the next question. The third worked example, this time we've got g of x, which is 2x cubed minus 5x squared plus ax plus a. So we're told that x plus 2 is a factor of g of x, and based on that, find the value of this constant a. So about the Factor Theorem, we'd be a bit stuffed here. The main thing is to note that if x plus 2 is a factor of g of x, so if x plus 2 is a factor of g of x, then therefore what this means using the Factor Theorem is that g of minus 2 is a root of g of x. In other words, g of minus 2 is equal to 0. So what we can do is sub in minus 2 and arrive at an expression for this which we can solve. So g of minus 2, we know it's going to be equal to 0, but we can see what drops out when we input x being minus 2. We'll have an expression which we can set equal to 0 and then solve. So g of minus 2, we're going to have 2 multiplied by minus 2 cubed, minus 5 multiplied by minus 2 squared, plus a multiplied by minus 2 plus a. So we can obviously just neaten this up an awful lot. Minus 2 cubed is minus 8. 2 times minus 8 is minus 16. Minus 5 times minus 2 all squared. Minus 2 all squared is 4. So minus 5 times 4 is minus 20. A multiplied by minus 2 is minus 2a. And plus a is just plus a. So we have minus 2a plus a, which is minus a, and over here minus 16 minus 20, that's minus 36. So minus 36 minus a, and we knew that g of minus 2 equals 0 using the Factor Theorem, and so this, which equals that, must also equal 0. So now we can go forward and solve for a, which is really easy. So if you were to add a to both sides, we'd see that a would equal minus 36. And the last question, which involves a graph sketch, is first of all we need to factorise f of x fully. So this one is a bit of a stranger example, but also a common one. We need to use a Factor Theorem, but we're not told anything or given any hints for this. So sometimes what we need to do, as we need to do in this case, is use trial and error. And so just trust that if this is set for you in an exam, it's a question on factorising, there will be an easiest route you can find. So as a general rule, try x being 1, 2, 3 and 4. If that doesn't work, don't go higher. Try -1, -2, -3, -4. And by trial and error, you'll find a factor. So for this first step, all we're going to do is use trial and error just to find one route. Just find one route, then we can find the next using division. So let's try f of 1. Is that a route? Is that going to give us 0? Well, 2 times 1 cubed is 2, minus x squared is -1 squared, which is -1. -5 times 1, -5, -2. I don't even need to work out what this is, okay? All I know is that it's definitely not equal to 0. That's all I'm interested in. That's not going to work, so we can bin that as an option. Let's try f of 2 though. F of 2, we're going to have 2 times 2 cubed, which will give us 16, minus x squared, so -2 squared is -4, minus 5 times 2, -10, -2. This looks a bit more hopeful, doesn't it? 16 minus 4 minus 10 minus 2 does equal 0, so big tick. Now we can use a factor theorem. If f of 2 is 0, we can therefore say that x minus 2 must be a factor of f of x. So we've worked out something that will divide into f of x exactly. So now we can use polynomial division, either method, whichever one you prefer from what we've talked about before. So I'm going to divide x minus 2 into 2x cubed minus x squared minus 5x minus 2. So 2x cubed divided by x, that just gives us 2x squared. Now we multiply. 2x squared by x minus 2 gives us 2x cubed minus 2 multiplied by 2x squared gives us minus 4x squared. Got my tongue tied. So now we can subtract. This cancels. Minus x squared minus 4x squared is minus x squared plus x squared, which gives us 3x squared. Next we bring down the next term along, which is the minus 5x, and we go again and divide. So minus 3x squared divided by, 3x squared rather, divided by x gives us positive 3x. Now we multiply. 3x by x gives us 3x squared minus 6x. Next we subtract. This cancels as always. Minus 5x is minus 6x is minus 5x plus 6x, which just gives us an x. And we bring down the final term, which is negative 2. Then we go again. X divided by x is obviously just 1. Multiply 1 by x minus 2, we just have itself. Final step, subtract. And as you'd expect, because we knew that x minus 2 was a factor, we have a 0 remainder. And so what this tells us here, all of this tells us that f of x must equal this x minus 2 multiplied by 2x squared plus 3x plus 1. So we're nearly done. The only thing is, we need to think, will this second bracket factorise again? The quick answer is it will. So let's think how and why. So what we need to do here, we can leave the first bracket as it is. This green bracket, we can use the AC method. So multiply the 2 by the 1, which gives us 2, and think of two numbers that multiply to 2 and add up to 3. Those two numbers are going to be 2 and 1. So we can rewrite this 3x in the middle as a positive 2x and a positive x, and then a plus 1. So leave the x minus 2 as it is. This one, 2x squared plus 2x, has a common factor of 2x. So we can put this into 2x brackets x plus 1. Then the x plus 1, that's just one lot of itself. So we can say it's plus 1 lot of x plus 1. Finally, then, we have x minus 2. We can put the 2x and the plus 1 into its own bracket, and the x plus 1 at the end. And so that's f of x fully factorised. It now says for part B, hence sketch the graph of y equals 2x cubed minus x squared minus 5x plus 2, where y, as you can see, is f of x. So we're just going to sketch f of x, and we can use this factorised form to help us. So let's get the axes ready. So what we know here, because it's factorised, we can work out the roots. So let's just write this here first of all. So the roots are going to be where x equals 2 from this bracket, where x equals minus a half, looking at this bracket, and the last bracket where x equals minus 1. So we can use this to build our sketch. We also know where the y-axis intercept is going to be just by seeing where the constant term is. Plugging in x is 0, the y-intercept is going to be at minus 2, and it's a positive cubic, so it's going to have the characteristic shape like this, going upwards. It's going to cross the x-axis at 2, minus a half, and minus 1. So let's just build this in. So it's going to come up through minus 1, it's going to go down through minus a half, cut at minus 2, come back up like so, and cross again here where x is 2. So we need to label this on. So that's where x is 2. Here x is minus 1. Here x is minus a half. And the y-axis intercept down here is minus 2. And that will do for our sketch. And so that's another use of factorising quadratics and polynomial division and the factor theorem. So it all comes together in this lovely way. So that's all from me. Now it's over to you. I'd like you to try these questions, please, if you can. Exercise 7C in the books, starting at page 145. So try these, and always double check each and every question you do using the back of the book. If you get them wrong, try and correct them yourselves. If you're not sure where you've gone wrong, as ever, ask me. Please do. So carry on working hard, and stay tuned for the next session on this topic, which is going to be lesson 7.3, I've called it. So once again, thanks for tuning in, thanks for working hard, and I'll hope to see you all again very soon. Bye for now.